We're now going to be looking at the series of sections of Chapter 5 that have to do with energy and chemical reactions. Earlier, we looked at temperature changes for substances and also just phase changes. Now we're looking at chemical changes. And so we're going to look at enthalpy change for chemical reactions and how we describe those using thermochemical equations. And then we'll look at how enthalpy changes are actually determined. They're determined experimentally using calorimetry. And then we'll look at a pair of related items, Hess's Law, which has to do with which is essentially linking enthalpy changes for multiple reactions, and how that is made useful through the use of enthalpy of formation. So just a quick review, we've looked at lots of different types of energy. There's lots of different ways we can measure energy, lots of different energy units. When we study energy chemically, the main unit we use, at least at this stage, is enthalpy. And the reason we use it is it's easy to measure, because it's the heat exchanged by the system and the surroundings when a process occurs under constant pressure, which means you can do it in an open container. You don't have to build up or lose pressure when the reaction happens. And remember that there are energy diagrams that relate stability and energy and enthalpy for reactions. In this case, the reactants are higher in enthalpy than the products, so the reaction loses energy, so it's exothermic. And it also means that the products are more stable, the reactants are less stable. Okay, now we turn to thermochemical equations. The idea is when a reaction happens, energy is, or heat energy at least, is generally almost always released by the reaction or absorbed by the reaction. That is determined, or that is written as a delta H value, enthalpy change value. So in this case, we have burning of a hydrocarbate, a carbohydrate, with oxygen. It makes CO2 and water. It's a combustion reaction. And enthalpy decreases, which means the products are more stable than the reactants. And that's an exothermic reaction, meaning energy is released. And so another way to write that would be that the products react to give the reactants react to give the products plus energy. So the fact that energy is released, it's like a product. Delta H is negative. Conversely, if you have a reaction that has a positive delta H value, it's endothermic. That means the reactants have to absorb energy in order to make the products. The heat energy would be listed as a reactant. It's something that's used up, like the reactants are used up, when the product is formed. And so these are called thermochemical equations. We can use that in a practical way to just talk about or to determine how much heat will either be absorbed or generated when a certain amount of reaction happens. We have here the thermochemical equation, or the equation and the delta H value for the combustion of propane. If 0.25 moles of propane are burned, what quantity of heat, that is how much heat is produced? And we know that for this reaction, as written in moles, 2,220 kilojoules is produced. So to do that, you would say 0.25 moles of propane, which is C3H8, times 2,220 kilojoules of energy released. The released you know because of the negative sign there, per 1 mole of propane. And it's 1 mole of propane because there's 1 mole of propane reacting in this balanced equation. And so that then tells you how much energy is released. 0.25 times 2220. 555 kilojoules are released. If you had the same kind of thing, but you were talking about how much CO2 is produced, 1.6 moles of CO2 are produced, you would write 1.60 moles of CO2 times 2,220 kilojoules are produced, that is released, for every 3 moles of CO2. And the fact that that comes about because 3 moles of CO2 are produced in this balanced reaction. And so when this reaction happens as written, 1 mole of this, 5 moles of this, 3 moles of this, 4 moles of this, that much heat is produced. So that's the amount released. And in that case, it's 1.6 divided by 3 times 2220, 1,184 kilojoules are released. Okay. When you're working with delta H values for reactions, you can actually modify the way the reaction is written, and when you do that, the delta H value will change for the new reaction you've written. And so, for example, if we take the reaction between hydrogen and oxygen, 1 mole of hydrogen and half a mole of oxygen goes to make 1 mole of water. Delta H for that is minus 241.8 kilojoules. If you double that reaction, that is, you multiply the entire reaction by 2, you'll have 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water formed. The delta H value is also multiplied by 2. So if you multiply a reaction by a constant, either 1, 2, 3, 4, a half, a third, whatever you do to multiply through that reaction by that constant, you do to the delta H value to get the delta H of your new reaction. The second rule is that if you reverse a reaction, here we have hydrogen and oxygen reacting to make water. If you just reverse the reaction and swap reactants and products and write backwards, you have the same numerical value for delta H, but you've changed the sign, which makes sense. That makes sense in the sense that if you have reactants here and products here, and you're going down in energy, if you just swap them, you'll have products here, reactants here, and you'll be going up that same amount of energy. Same energy change, just in the opposite direction, so you change the sign. Here's an example of how that would work. If you know that the reaction of SO2 plus half an O2 to SO3, all this is gas phase, has an enthalpy change of minus 98.9, what would it be for this reaction? And what you have to do is, what have you done to this reaction to get to this one? Well, one thing you've done is you've reversed it. So you've swapped the reactants and products, so we'll change the sign. And the other thing is we've multiplied by 2, because you now have 2 SO3s instead of 1, 2 SO2s instead of 1, and 1 O2 instead of a half an O2. And so our new delta H is going to be minus 98.9. Change the sign for that, so make a negative for that, times 2. So it'll be plus double 98.9. So it's plus 197.8 kilojoules. And it's kilojoules per mole, meaning the moles written in that reaction. The next thing we want to do is just talk about, very briefly, about where delta H comes from. Where does enthalpy change come from? And on a chemical basis, it actually comes from bond energies. And delta H is the energy needed to break bonds between molecules, between atoms and molecules, minus the energy released when you form bonds. When you form bonds, you release energy. When you break bonds, it takes energy. And so it's the energy required to break all these apart, in this case for making water out of hydrogen and oxygen. That's positive, that's endothermic. And negative, that is released, it's exothermic when you make those new bonds. And so if you know how much energy it takes to break those bonds, which we'll be doing later in the course, you can do that calculation. And so for this particular case, the energy to break the O2 bond is 498 kilojoules. The energy to break each H2 bond is 436, so it's 2 times that. And you make 4 OH bonds. Each of those is 436. And those are negative because 4 bond forming is exothermic. And so when you add all that up, that's where the minus 482 comes from. We'll do this more later on in the semester when we're talking about bond energies, but it was important to just say where that comes from now. So that works for gas phase reactions. If you have things that are happening, as most reactions do, either in solution or one of them's a solid, that bond energy calculation doesn't work because there are energy between the solvent and the molecules and energy between the molecules and the solid state. So that delta H using bond energy only works for gas phase reactions. Most reactions, in order to find delta H, to find the enthalpy change, you need to do experimentally. You need to do experiments to find that out. And the experiments that are done for this are called calorimetry. And the way it works is you run the reaction in a way that you can measure how much heat is exchanged between the system and the surroundings. And if you know how many moles react and you know how much heat is exchanged, you know then the delta H. And to do that, you use a vessel, a reactant container called a calorimeter. There are 2 types of calorimetry, or types of calorimetry experiments. One is where the reaction is done under constant pressure, meaning it's open to the atmosphere. So you can't build up pressure. The other is constant volume, which is closed to the atmosphere. If you actually do constant pressure, you're measuring delta H. If you do constant volume, you're actually measuring delta E for the system. Constant volume calorimetry uses a bomb calorimeter, which is expensive and needs to be done very carefully. So this is done much less than constant pressure calorimetry, which is much easier to do. So we'll look at each of those cases. When you do constant pressure calorimetry, the easiest way to do it is just use insulated styrofoam cups. And in this case, we're going to take 4.50 grams of ammonium chloride. We're going to take 53 grams of water. We're going to add the 4.5 grams of ammonium chloride into that. And when you do, the temperature goes down. The temperature drops from 20.4 degrees to 15.2 degrees, which means it's an endothermic reaction. And we want to calculate delta H for that reaction. The way you do it is delta H is going to equal the number of joules exchanged divided by the number of moles of NH4Cl. So the moles of NH4Cl we can determine by taking our 4.50 grams NH4Cl and multiplying that by 35.45 plus 4.04 plus 14, 53.49 grams for 1 mole. 4.5. That comes out to 0.0841 moles. So that's how many moles react. The joules that are produced or that are absorbed are determined by our same equation we used earlier for temperature change. The number of joules is going to be equal to the specific heat of the substance changing temperature times the mass in grams times the temperature change. The specific heat, we're told to use 4.18 joules per gram degree, and that makes sense because most of what is being heated is water, and that's the specific heat for water. The mass is the sum of the water and the ammonium chloride, so that will be 57.50 grams. And the temperature change is 20.4 times 15.2, 5.2 degrees. Now the temperature went down, so you would normally write that as a negative. My advice is just do everything as a positive. You know the reaction is exothermic or endothermic, and just put the correct sign on when you're done. So that's 4.18 times 57.5 times 5.2. So that's 1,250 joules. So our delta H value then is 1,250 joules divided by 0.0841 moles of ammonium chloride. And that comes out to 14,900 joules, which is 14.9 kilojoules per mole. And that's how you do constant pressure calorimetry. Notice one thing you're assuming here is you're assuming the cup has no temperature change. And what you're really assuming is that the cup doesn't absorb or give any significant amount of heat. For a bomb calorimeter, you normally can't do that because it's actually a much bigger, much more hefty vessel, and the calorimeter itself will also change, will also involve some heat to either raise its temperature or if its temperature goes down. And that's given by a calorimeter constant, which is a number that goes along with the piece of equipment. When you get the equipment, you measure that, and you know that then for the piece of equipment. And so in this case, we're going to react hydrazine, N2H4, with oxygen. And when you do that, if you use 0.5 grams of hydrazine, the temperature goes from 20 degrees to 22.8 degrees if the calorimeter holds 600 grams of water. So the calorimeter here, the reaction happens in here. This is filled up with water. You've got 600 grams of water in there. And so the energy that is produced both is used both for heating up the water and heating up the calorimeter. So the joules associated with the water will be 4.18 joules per gram degree. That's the specific heat for water, times 600 grams, that's our mass of water, times the temperature change, which is 2.8 degrees Celsius. And so the energy associated with the water is 7,022 joules. The calorimeter takes 420 joules for each degree to go up. So it's 2.8 degrees Celsius times 420 joules per 1 degree Celsius. So that's 1,176 joules to warm up the calorimeter. So the total is the sum of those, which is 8,198 joules, and those are released because the temperature went up. So our net delta E will be negative because we know the reaction's exothermic because the temperature went up. So what we then have to do is we have 8,198 joules. We have to put that over the moles of hydrazine reacting. So it's 0.500 grams of hydrazine times 1 mole over its molar mass, which is 2832.04 grams. And when you do all that, divide it by 5 times, you get 525,000 joules per mole. And you know that it's negative because the temperature goes up, so it's exothermic. So delta E is minus 525 kilojoules per mole of hydrazine reacting. All right. The next thing is Hess's Law. And the general idea for Hess's Law is this is used to relate a series of reactions that can be added up to a final reaction. And the idea is that if you have a series of reactions that you can add up to give some net reaction, the enthalpy change for the net reaction equals the sum of the enthalpy changes that for the reactions that have been added. So let's look at an example of this. If you take carbon and oxygen and hydrogen, those can react to make carbon monoxide and water in the liquid state. Those carbon monoxide and water can react to make H2CO, which is formaldehyde, and formaldehyde in the gas form, and formaldehyde in the gas form can condense to make formaldehyde in liquid form. And each of those processes has a delta H value. What you can do then is you can add up those three reactions. And if you do that, notice certain things will cancel. You have a CO here and a CO here, they cancel. You have a formaldehyde in the gas phase there and there cancel. So your net reaction is carbon solid plus 1/2 O2 in the gas phase plus a water in the liquid phase goes to make formaldehyde in the liquid phase. And delta H for that is going to equal the sum of the delta H's for these reactions that we added up together. So we have this new reaction here, which we've never done. We've never actually done this reaction. But you can figure out the delta H for it from knowing the delta H's of these other reactions that you do know. And so delta H for that will be minus 110.5 plus 33.7 minus 62.9. So if you add all those up, it'll be that many kilojoules. It will be delta H for that reaction. So that's the idea of delta H of Hess's Law. Hess's Law is called a state function, which means that essentially what you're saying is it doesn't matter how you get from these starting materials to that product. The difference only depends on where you start and where you end. That's what a state function says. Only the initial and final states matter, not the pathway to get there. That's why you can use these reactions to tell what delta H is for this, even though this reaction might not happen this way. In fact, it almost certainly would not. Okay, so when you're using Hess's Law, what the key is to be able to figure out how to add up reactions that you know to get the reaction that you want. And so here's an example of that. Here's two reactions we know, and we want to find delta H for this reaction that we don't know. The key is to use these reactions here in a way that works. And what you have to do is you have to look for the reactants or products and make sure they end up on the right side. So we know that we need tin chloride on the left, tin 2 chloride on the left. So this reaction 1 is the only place where we have tin 2 chloride, and it's on the left. So we'll use reaction 1 as is. So let's write reaction 1 down. SnCl2, I'm going to leave off the states. Cl2 SnCl4, and delta H for that is minus 195 kilojoules. Now notice we need TiCl4, titanium tetrachloride. We need that on the left as a reactant, but in this reaction, in reaction 2, it's on the right, which means that we're going to have to turn reaction 2 around. So it's minus reaction 2, and so we'll turn that around, so we'll have TiCl4. That now goes to make TiCl2 plus Cl2. And delta H for that now will be, this was minus 273, but we've swapped it around, so now it's plus 273 kilojoules. Now, if you look at that, if we add those two up, what we end up with is the chlorines cancel. We end up with SnCl2 plus TiCl4 goes to make SnCl4 plus TiCl2. And so we have the reaction we wanted. And we did that by finding a way to combine these reactions to get that. And delta H for our reaction that we want will be the sum of these two here. So minus 195 plus 273 kilojoules. So that's how Hess's law is used if you know a particular set of reactions that you can use. The way Hess's law really comes into use, though, is through the concept of enthalpy of formation. Enthalpy of formation is the energy change, the enthalpy change, for a particular type of reaction called a formation reaction. And a formation reaction is a special reaction where you're taking elements in their natural states, their standard natural states, and forming 1 mole of a compound of interest. So it's for the formation of 1 mole of a compound from its elements in their normal states. And so here's an example of a formation reaction. We're making dinitrogen pentoxide, and we're making it using nitrogen in its normal state, which is nitrogen normally exists as N2, oxygen in its normal state, O2. Notice that you often will have to use fractional numbers of moles in your balanced equation, and that's perfectly okay. So we need 5 oxygen atoms, so we need 5 moles of oxygen in our reactions. We need 5 moles of O2. We happen to only need 2 moles of nitrogen, so we can use 1 mole of N2. So the delta H for this particular reaction is the delta H of formation for N2O5 because this is a valid formation reaction. So you would find in a table the heat of formation, delta H of formation for N2O5 to be minus 43.1 kilojoules. You can write other reactions that make N2O5 or N2O4 or whatever. Here's one that makes N2O4. 2 NOs react with O2 to make N2O4. This forms that compound, but this is not a formation reaction. So it is not equal to delta H of formation. And it's not a formation reaction because we're not using elements, only elements to form it. We're using oxygen, but we would be needing to use N2 here to do the to be making this if this was going to be a valid formation reaction. So we have big tables of these standard heats of formation, enthalpy of formation values, and you look them up. And the reason it's going to be useful is you'll be able to determine the delta H of any reaction involving these particular compounds, as well as elements in their natural states. Delta H of formation for any element in their natural states equals 0. And the reason they equal 0 for elements in their natural states is, by definition, the heat of formation is to make something from elements in natural states. If it's already an element in its natural state, you don't need to make it, and therefore there's no energy involved. So what you're going to do is we're going to use these for determining enthalpy of reaction for lots of different reactions, hundreds and thousands of reactions. And here's an example of another enthalpy of formation reaction of where all these numbers come from. So it says here that the enthalpy of formation for potassium chlorate is minus 397.7. What you can do is you can write down what reaction that pertains to. And so if you're going to make 1 mole of potassium chlorate in the solid state, to do that, you have to find what elements these are and use them in the right amounts. So you're going to need 1 potassium, and potassium's natural state is a solid. You need 1 mole of chlorine for every mole of potassium chlorate. Chlorine is a diatomic, so you're going to have to use a half a mole of chlorine gas. You can't just use 1 chlorine there. That's not okay, because chlorine actually exists as Cl2. You need 3 moles of oxygen. Oxygen exists as O2, so which means you're going to need 3.5 moles of O2 gas. And so that is the formation reaction that pertains to, that goes along with the heat of formation value. So delta H for that reaction is the delta H of formation, which is minus 397.7 kilojoules per mole. All right, so now here's how we use it. The idea is actually an extension of Hess's Law. It's a special case of Hess's Law, where let's say we're looking at this reaction, CH2F2 plus 2 HCl's. These are F's, those are Cl's, these are hydrogens, and the central atom there is a carbon. Those two react to make essentially it's an exchange reaction where the chlorines go on the carbon compound and the fluorines end up with the hydrogen. The way we do this, the way you use this in terms of using Hess's Law and using enthalpies of formation values, is you imagine the reaction happens a particular way, even though it doesn't actually happen that way. It doesn't matter what mechanism the reaction goes by, what pathway it goes by. But basically what you do is you split up the reactants into elements. You take the reactant molecules and split them up into elements, and then you take the elements and you form the compounds in the products. And so if you look at the second part here, the energy change for this process is going to be the sum of the enthalpy of formations values for the products. Because what you're doing is we're making the products from the elements that they're made of. And so the enthalpy to do that second step there, step 2, is the sum of the enthalpies of formations for these compounds, because that's what they're doing. They're being made from their elements. The process to get there, step 1, is the opposite of that. It's essentially taking the compounds and making the elements out of it. So it's the opposite direction. So the enthalpy of that first step is minus the sum of the enthalpies of formation for the reactants. The overall process will be the sum of step 1 and step 2. Taking the compounds and making them into elements, taking the elements, making them into the products. Remember, the reaction doesn't happen this way, but we can think of it happening this way because of the fact that Hess's Law works and that enthalpy is a state function. It only matters where you start and where you end. You can imagine any pathway to get there. So therefore, the central reaction enthalpy change is going to always equal the sum of the heat of formations of the products minus the sum of the heat of formations of the reactants. And you just look them up on the table and add them up. So let's look at an example here. We have 2 carbon monoxide in the gas phase, reacts with an O2 in the gas phase to make 2 CO2s in the gas phase. What you do is you look up these numbers on our chart. So you go to our chart and you look up the carbon monoxide, and its enthalpy of formation is minus 110.5 kilojoules per mole. For oxygen, it's 0 because oxygen's an element. And for carbon dioxide, it's minus 393.5. And so those are back on this table here. And then what you do is you add them up. You take the products and you add those up. So the products are just the 2 CO2s. So it's 2 times the negative 393.5. From that, you subtract the sum of the reactants. The reactants are 2 COs, so that's 2 times minus 110.5 plus the oxygen, but that's 0. And so when you add that up, you get the overall net delta H for the reaction. Now, something to be careful about is the biggest trouble students have with this kind of problem. It's conceptually very easy. The 2 things that they trouble with is forgetting to account for numbers of moles of reactants or products in the balanced equation, and just being sloppy with signs because you're subtracting a negative, and it really helps to just kind of jot down pieces along the way. So calculate this first, write it down, calculate that first, write it down, second, write it down, then subtract them. So do it that way. And that ends our exploration for energy and reactions.